So we looked at certain properties of full binary trees. Full binary trees. And let's look at the properties of these full binary trees. We said, what were the properties that we looked at? We said, for example, if let's look at full binary trees. If there are I internal nodes, then the number of leaves L is I plus 1, and I internal nodes same I internal nodes, then the number of nodes in the tree, is n equal to 2i plus 1, and so on. Okay, and if then of course the other relationship, if n nodes are there in the tree, then then I is equal to n, number of internal nodes equal to n minus 1 over 2. So let's say there are other properties that we can have. L is equal to n plus 1 over 2, where L is leaves, n is the total number of nodes. Okay, nodes in the tree. And from this property D, we can say n is equal to 2L minus 1. And finally, we can also have a property which says I is equal to L minus 1, or I plus 1 equal to L. Okay. So basically, if you know n, then you can find L, and from L, you can find I, because N, L, and I are interrelated in a full binary tree. Okay. So let's do one or two proofs, and the rest I will allow you to take care. Okay. 1 minute. Okay, so let's look at this. One or two proofs over here, and okay, let's take this first part. First part is L equal to I plus 1. We can use induction on the number of internal nodes. Internal nodes I. So let us say that there is a set S of all integers that is greater than or equal to for all integers I that is greater than or equal to 0, such that T is a full binary tree with I internal nodes. Okay. Then what do you want to show? L is equal to I plus 1 for this tree. What is L? L is the number of leaf nodes. Let's take an example first. So let's say this is a full binary tree. So this one has two internal nodes, 1 and 2. Therefore, total number of leaf nodes should be I plus 1, 2 plus 1 equal to 3, which is equal to L. Okay, that's what we have. Now, let's try and prove this. Let's say the base case I equals 0, L is equal to I plus 1. Since root is the only node, okay, it has no children, okay, therefore it becomes a leaf node. It becomes a leaf, and the tree is a full binary tree. This implies what? One leaf node. This implies I, which is 0, belongs to S. What is the hypothesis that we have? Induction hypothesis. Assume for some k greater than or equal to 0, every I from 0 through k is in S. Then that is what this means is that if T is a non-empty binary tree with I internal nodes for 0 less than or equal to I less than or equal to k, then L is equal to I plus 1. Let's prove this now. So let T be a full binary tree with k plus 1 internal nodes. Okay, we're adding one extra internal. Let L and R be the left and right subtrees. Okay, and let IL and IR be the corresponding number of internal nodes. Internal nodes, respectively. Okay. Now, neither L or R can be empty. Since every internal node sorry. Why so? Because we removed the we can take care of, we've already taken care of the base case, okay? With 0 I, then k greater than equal to 0 or okay. Then what we do is by the every internal node in L or R has, and every internal node in L or R are internal nodes of T. Nodes of T. And T has one additional internal node, the node root. Okay. Actually, we will change this to the greater than 0. We already saw the this case. Because we want the left child and so k plus 1 equal to IL plus IR plus 1 by the induction hypothesis. L must have IL plus 1 leaves and R must have IR plus 1 leaves. Every leaf also has that. Every leaf in T is also a leaf in L and R. Okay. We have IL plus IR plus 2 leaves. But IL plus IR equal to K. Therefore, T must have K plus 2 leaves. Okay. That means K plus 1 also belongs to S. S belongs to 0, infinity by not induction.